Good morning, everybody. Today we will have the talk by Dr. Anne Straume from ESA, from the Space Agency, European Space Agency, and she will talk about the ENVISION mission to Venus, discovering why our closest neighbor is so different. So Dr. Anne Straume will be introduced by Dr. Francisco Gonzalez. Please, Francisco.
Hi everyone, and thanks for coming to this seminar. So it's our pleasure to welcome Annegret Straume from the European Space Agency, who will be talking us about the ENVISION, an exciting mission in which the IAI is somehow involved. So Annegret Straume, after her PhD in meteorology in 1998 at the University of Bergen in Norway, and then she has worked on several topics related to the Earth atmosphere, including pollution transport, the impact of changes in the ozone layer to the stratospheric dynamics, and satellite observations of greenhouse gases and atmospheric winds. She started to work at the European Space Agency in 2004 as project scientist for the ESA Doppler Wind LiDAR mission called AEROS. She also defined and supervised several studies in other science areas, among others, one on synergistic observations of methane and carbon monoxide on Earth and Mars. In January this year, she started as the project scientist of ESA's next mission to Venus, ENVISION. So the floor is to you. Thanks for the invitation.
So thank you very much for this very nice introduction. So indeed, I'm the project scientist for ENVISION, just started on this mission early this year. And the ENVISION mission is the first mission to ESA to Venus from ESA since about 10 years. And I will talk more about that later. Let me see, the button is working. It is not working. It looks like I can stick. Okay. Yes, it is working. Could you try to again with the? I will try again. Yes, okay. It's working. Thank you, Gabriela. So of course, I'm not working on this mission alone. In this slide, there are some names on from our study science team, and Gabriela Gilli, who kindly invited me here and is working in your institute. She's one of the members of the science team for ESA. So these people are Venus experts, and they are also those that have, at least some of them have proposed this mission to ESA earlier, and then ESA has adopted this or has selected this mission now for study, and the adoption of this mission will come in 2024. So these scientists are supporting the missions in different phases. We're now in the so-called phase B1, where we look at the feasibility of the study, and you can see all the names of the co-authors here. Also in ESA, there is a big team of engineers, and the names are shown here on the slide, just some of them. These are just a few, but there are many more. And the ENVISION mission is a mission also in close collaboration with NASA, who are providing one of the instruments on board. And also mentioned in these slides are some of the names of the people at NASA who's working on this mission. And last but not least, we also have the teams in industry, and also the science teams in the different institutes, amongst others, also the IAH, who are working on developing the instruments and the spacecraft. So I'll first say a few words about Venus. Probably many of you know this before, but perhaps some of you are not so familiar with the planet. So Venus is an Earth-like planet, quite similar in size, and it is our nearest neighbor on the inner part of the solar system, the inner part of Earth. Its rotation period is, however, very slow. It's 243 Earth days, and it's also rotating in the opposite direction of what Earth does, so backwards, if you say. So it's slower than a Venus year, which is 225 Earth days. So it's very different in that respect. Also, the surface pressure is very high. It's 90 bar compared to on Earth. You have a surface pressure of 1 bar. And also the temperature of the air close to the surface is almost 470 degrees. So it's very hot on the surface. The atmosphere is not very hostile. Most of it is CO2, actually about 97% of it. And CO2, as you probably know, is a very strong greenhouse gas. There is then some amounts of nitrogen, and then on the sub-percent level, you have different trace gases such as water vapor, SO2, etc. What's also very striking about Venus is the massive cloud deck which is covering the planet. You can see that in this image here on the right of Venus. And that cloud deck is very dense. So on the left-hand side here, you can see an artist's impression of how it is on the surface of Venus. So it's daylight there, but very little compared to on Earth. So it's pretty gloomy, if you like. And this cloud deck is having two functions. First of all, there is less solar light coming to the surface than on Earth, but it's also trapping the emitted radiation from the planet itself, which makes it such a hot environment. Also striking is the superrotation. So the winds on Venus, they're going in the east-west direction, are very, very strong. And that's also very different circulation than you have on Earth. So it's therefore challenging to land something on the surface and Venus, and let alone to operate something there. It's hot, it's toxic, and also there is little sunlight. So that means that operating things like solar panels, like the rovers on Mars are using, that's virtually impossible. It's not very effective. But there has been landers on Venus in the past. On the bottom here, you can see an image which was taken by the Venera 9 lander by the Soviet Union back in 1975. It was the first image of the surface of Venus. Very spectacular and showing a very rugged planet. And this mission could operate for a few hours as long as the battery was lasting. So this mission used actually batteries to be able to operate on the surface. Also, Venus has no moon, and it has virtually no magnetic field, which is then leading to it to be poorly protected from the solar winds, which are also eroding the atmosphere quite substantially. There are also no oceans on the surface. It's dry, and there is low water vapor in the atmosphere. However, there are a large variety of terrains on Venus, including rifts and mountains, impact craters, volcanic craters. Here, this big image is a topography map from the NASA Magellan mission, which was flying in from 1989 to 1994. And the colors here are indicating the altitude of the surface from -2 kilometers up to 10-kilometer altitude. So it's quite a high variety in the terrain on the surface. And another particular thing is that the ratio in the atmosphere between deuterium and hydrogen is quite high. And this scientists believe are hints to that there may have been a strong water loss in the planet in the previous or in the past during its history. And this is very interesting because that could indicate that maybe there was liquid water on the surface before, or at least that the planet may have had quite a different climate potentially in the past. So some of the things we don't know about Venus is how the interior of the planet is working. So there's a sketch here on the right, which shows the core of the planet and the magma and layers and the surface over here with the different features that you can find on the surface. So things like the core size and the state of the core, it is most probably solid, but this is also not 100% certain. And also how the surface was formed and how old it is. These are questions that are still open for Venus. Earlier observations of the planet, for instance, from the NASA Magellan mission I showed you the topographic map of before, show that there are very few impact craters on the surface. Now that can maybe be explained by the fact that the surface, the atmosphere is so dense, but that's not enough. There are still fewer impact craters that we would expect from a planet with such an atmosphere. There are also no signs of tectonics, plate tectonics. So it seems that Venus has a pretty solid lid, which is not dynamic. And also the higher altitude tessera regions are heavily deformed, however, by tectonic deformation. So the question is, how could they be so deformed? These high lands that you show in the that you saw in the figure before here with the color purple, the purple colors, sorry. Whereas the lowlands seem to be quite with very few tectonic features. So the hypothesis is that actually there have been some few catastrophic resurfacing events of Venus in the past. The last one has been estimated to be less than 1 billion years ago. But the big question is, how come that these tessera, these higher elite regions, are then so deformed and show traces of tectonic activity? Also, a question is, as I mentioned before, has there been any water on the surface in the past? This figure is showing you on the vertical axis the solar efficient temperature. Sorry, I'm forgetting. I'm having 2 slides here. So I'm reading on my screen. So this figure shows you the vertical axis, the stellar effective temperature over here as a function of the distance from the star. And then you have different exoplanets and how they are located with respect to the distance to the star and as a function of the star temperature. So you can see Earth over here and Mars. They're both within the so-called habitable zone, whereas Venus, which is on the inside of Earth, closer to the sun, is already in this arid hothouse region. However, in the distant past, the sun was less bright than it is now. So then Venus would, if you like, would move closer down to the green area. So it could have been habitable potentially in the past. And also had liquid water on its surface. So there are different models on how Venus has evolved through time. And for instance, there is it's a very nice in-depth paper by Savik Jilman, who's been modeling different options for how Venus's evolution was going through time. So one of the theories on how Venus become as it is today is the so-called dry Venus scenario. Here you have very high CO2 concentration forming after the magma ocean was cooling down, and you get the formation of the surface. And the high CO2 concentration, it's a strong greenhouse gas, then give you very high temperatures, which is causing the water vapor, which comes from the volcanism, to raise, and then water vapor is lost to space through different processes such as photodissociation and the other processing, the reactions with the strong solar winds. Another scenario is the wet Venus, which is shown over here. So perhaps a CO2 got trapped inside of the planet in the early phase. There was less CO2 after the planet formation and the formation of the surface. We had more nitrogen concentrations, and water vapor from volcanism could therefore have condensed on the surface because it was less hot. However, at some point, the CO2 levels may have risen, or as the sun was becoming brighter, there was an enhancement of the evaporation of the water vapor on the surface from the potential oceans that would have been there. And water vapor is a very strong greenhouse gas. It's very effective to store energy in the atmosphere. So this would have accelerated the heating up of the planet, the evaporations from the ocean, and the planet just gets hotter and hotter and hotter with time. And then it means that the planet cannot cool, it cannot radiate as much to space as it is heating from the atmosphere itself and from the surface, and you get the so-called runaway greenhouse effect. And that may have led to the water vapor in the atmosphere also going higher up in the atmosphere and getting lost to space by a different mechanism. So exactly whether Venus has developed via this dry Venus path or whether the wet Venus path, we don't know. The Earth has been moving towards this path here because the Earth has a lot of tectonic activity and is also further away from the sun. So here the formation of oceans was possible, and we still have that, as you know, in the present day time. So another question is whether there are active volcanoes on Venus today. So the very high concentrations or relatively high concentrations of SO2 in the atmosphere, it's higher concentrations in the Venus atmosphere in percentage than it is on Earth. And also the fact that we have a very massive cloud deck, which contains sulfuric acid droplets, that probably couldn't have been maintained if there was not active volcanoes on the surface. But it's not been absolutely certain that this is the case. So on the sketch here on the right, you can see a little bit of a sketch of how volcanism can lead to different sources of water vapor, SO2 and CO2 in the Venus atmosphere. So some of the water vapor and also the CO2 gets trapped on the surface, goes down and gets trapped into the rocks, and you have a cycling into the planet and out again from the surface processes. How much that is and exactly the details on how that's happening, that's not absolutely clear, and that's one of the things that the scientists would like to study also with the ENVISION data. Part of the water vapor and also SO2 is believed to raise up and feeding the cloud deck, which has, as I was mentioning, the sulfuric acid droplets and high CO2 concentrations. And then the water vapor is also moving slowly up to the upper part of the atmosphere, where you have the photodissociation of water vapor and escape of hydrogen. But in the past, there have been some indications that there may be active volcanoes also today. And that was shown by some measurements by the ESA Venus Express mission. This one was flying between 2006 and 2014 and measuring Venus from an orbiting platform. So two of its, instruments, one being the VIRTIS instrument, which was mapping the surface in the near infrared, because Venus has some spectral windows in the near infrared, which makes the thermal emission radiation to escape through certain wavelength. And this was exploited by the VIRTIS mission, and they could make maps of the surface temperature from this. And here there is some work from NASA JPL, which was correlating this thermal map with topography from the Magellan mission. And this is the Eden Mons volcano over here. And in one shot or one measurement that they did over that one, they actually saw elevated temperatures over this volcanic feature, which could indicate that it's maybe a volcanic eruption going on. However, Venus Express was only passing over this feature once, and that had to do with the orbit it was having. So there is a one-off observation like this. So it's not the smoking gun for this. It was also seen by another instrument on Venus Express called SPICAP, which was measuring SO2 concentrations above the clouds in the mesosphere, was that you had high variability in SO2 here on the vertical axes with respect to the time here on the horizontal axis. So you had quite high variability in SO2 during the mission lifetime. Such variability had also been seen from earlier observations here in the 80s and also in the early 90s. And that could indicate either that the SO2 variability is triggered by the dynamics inside of the cloud deck and in the atmosphere, or perhaps it could be an indication that there is a very variable volcanic activity down on the surface. However, how to link the surface volcanic activities with the variabilities of the atmosphere, that's one of the science questions that are looked at by Envision. So here on this slide, I'm mentioning the main questions of Envision. So it's really to address the history of the planet, how the surface and the interior of the planet has evolved over time. It also wants to look at the activity, how geologically active Venus is, both when it comes to tectonics, but also when it comes to volcanic activities. And it's addressing the climate of Venus to see how you can link geological processes with variability of the atmosphere and also explain better the climate. So I mentioned some of the previous missions to Venus before, but here are some more examples. On the left here, I'm mentioning the Mariner 2 mission, which was making a flyby of Venus in 1962. This mission was quite spectacular because it gave the first closer observations of the Venus atmosphere. And from these observations from Mariner 2, it was possible to determine the surface temperature, also the atmospheric pressure, and the fact that it has a very low magnetic field. On the right, you can see the Venera 9 mission that I showed you the image of the surface from before. That was really spectacular, but it didn't only, of course, image the surface. It was also probing the atmosphere as it was descending through the clouds and below the clouds, and was making profiling both of the cloud and the atmosphere below. There have also been many other Venera missions in the 1970s and in the 1980s. And also the US have had missions, a series of missions called Pioneer. Then there is the Magellan mission, which I showed you some topographic maps of before. And that was also a very spectacular and a very big step forward for Venus science, because for the first time, the radar on board was providing high resolution radar images, which gave surface topography information at the scale of 1 to 200 meters for the first time. And you can see an image over here on the left-hand side, which shows you some of the features and the differences in brightness temperature of the surface, which can tell you about the variability in the types of surface material that you have. On the right, you have the Venus Express mission from ESA that I talked about before. And it was giving some evidence that there could be active volcanoes, perhaps on Venus today. But also another thing that the thermal observations of the surface showed was that perhaps the planet's rotation is slowing down with time. So by looking at the topography measured by Magellan in the 90s and matching that with the thermal maps also made from Venus Express, they were really looking at how the surface was moving with time and how fast it was spinning. So that's also an open question, which this mission that we're having now, the Envision mission, can help to address. There is a mission at Venus right now, which is called Akatsuki, which was starting its measurements in 2015. This one is actually flying in a highly elliptic orbit and is looking at the clouds of the Venus cloud X, the upper cloud and the lower cloud, using different spectral bands. And it's used to track the movement of the clouds and to establish the meteorology of the planet. It has been speculated whether, sorry, I have not swapped the slide here, pardon for that. that some of the features seen by Akatsuki, because Akatsuki has been seeing some dark features of different sizes, in particular this narrow streak here. Some people have speculated that maybe this is even a plume coming from a volcanic eruption on the ground, but it could also just be a dynamic boundary which is causing this and causing variability in the thickness of the cloud deck. So these earlier missions, they have been addressing several of the science questions that are also questions for Envision, but they have not been able to answer them fully. And therefore, it's a lot of room for not only for Envision, but also for many missions to Venus in the future in order to home into these scientific questions and solve the riddles of the planet's evolution and also how it is working today. So coming to the mission itself, the Envision mission has several payloads on board in order to address all of these different scientific areas. As I was saying at the start, it's an ESA mission in partnership with NASA, where NASA is providing the VENSAR mission, which is a synthetic aperture radar, which will be mapping the surface, both with stereo images to get photography. It will also provide brightness temperature measurements and altimetry, and is also a polarimetric radar. So it will be able to give some information about the surface properties and different types of surface material. On board is also a subsurface radar, which is provided by Italy, the SRS. And this is the first time such a system is going to be flown on Venus. It has been flown similar system before, for instance, on Mars. And this will be probing the upper part of the crust of Venus down to a maximum of 1,000 meters. And it will look for boundaries and stratification of the surface. It will also give some information of the surface structures. And we have a radio science experiment, which is provided by France with contributions also from Hungary. And this one will be used to do gravity observations and also to provide observation in radio occultation using the communication system between the satellite and Earth. So it will probe the atmosphere and also tell about the gravity variability of the planet. On the right hand here, we have a spectrometer suite called VenSpec. It contains 3 instruments, starting with the top one, VenSpec H, provided by Belgium. It's a high resolution infrared spectrometer to map the chemical composition of the atmosphere below the cloud deck on the night side, but also will give some measurements above the cloud on the day side. And we have the VenSpec U. It's an ultraviolet spectrometer, spectral imager from France. And then we have the VenSpec M instrument, which is a near infrared mapping to look at the surface through the spectral windows of the cloud and the atmosphere. And of course, we have also a Spanish contribution to this mission. So your institute is giving the data handling unit, and you're also involved in different parts of the work from the VenSpec suite also scientifically. So this instrument altogether, they're really addressing Venus in a holistic approach. And this is the first time one mission is addressing all of these areas at the same time. From the inner core, the crust and the lithosphere, and the mantle, which is done by the radio science experiments. The morphology and the geology, which is being addressed by the VENSAR instrument. The shallow structures of the surface, which is addressed by the subsurface radar sounder, and mesospheric gases, volcanic gases, and atmospheric profiling done by the VenSpec suite and also the radio science experiment. And then we have the mineralogy and volcanic activity expressed by VenSpec M. This is showing you how Envision is flying. It is in a polar orbit. On the right here, you can see a Mercator projection map of the surface of Venus. So the North Pole and the South Pole are stretched here. And you can see in the dark area, you have the nighttime, and the lighter areas showing you where you have the daytime. Basically, the satellite is moving from north to south at a bit higher inclination than what's shown in the sketch here on the right, as an inclination of 89 degrees. So inclination of 0 degrees, that's close to the equator. The pointer is not working out well. And if you have a 90 degrees inclination, you're really flying from north to south over the surface. The altitude of the satellite will be varying. So in some part of the orbit, it will be at 220 kilometers above the surface. And in the opposite part, it will be at 510 kilometers. So it will be lower on one part and higher on the other part. Exactly where the higher and the lower parts will be of the orbit, that's still being defined at the moment. So you can see here an example of the Venspec M measurements. Due to the Mercator projection, it looks like it has a bigger footprint on the north and the south. That's not the case. It's the same all the time. It's just a projection. And as the planet below is rotating, with every orbit, you get a shift of the orbit track going like this, and slowly you build up the measurements of the planet. So the mission duration for Envision is 6 Venus 0 days, so that's about 4 Earth years. Coming to the individual payloads, this is an overview of the VENSAR, synthetic aperture radar. It's an S-band radar operating at 3.2 gigahertz. And this will obtain images at a range of spatial resolution. On the right-hand side, you can see a table with the specifications of the radar. And on the left-hand side, you can see how the radar is measuring along the measurement track as it flies in this direction. Under the satellite, you can see the track of the satellite on the surface, and the radar will measure slightly off track and image the surface. It will look at and search for changes in the surface to look at a potential activity. And it will do that by doing imaging of the surface at 2 resolutions, 30 meters. And also smaller parts of the planet will even go down to smaller scales, 10 meters resolution. It will then provide surface topography maps using stereo radar imaging and globally with radar altimetry. And it will also characterize the surface by colorimetric reflections and emission properties using both the SAR and the altimetry mode. It will not give a full global coverage because it's making these small resolution observations. There is also not enough data rate even to have higher resolution data downlinked to Earth, because there are also many other payloads on board that needs to use the radio communication. So it will be a targeted mission. But shown in the next slide, this is some example of possible targets that the SAR will be looking at, and not only the SAR, also some of the other instruments. So this shows possible regions covering tessera, craters, volcanoes, etc. And these will be imaged in a nested way by using different image resolutions. Also, some of them will be measured in polarimetry mode, and the radar brightness temperature, and also there will be thermal mapping by one of the spectral mappers, and also the subsurface radar will be looking at these regions of interest in order to get a holistic view and really to understand what type of material is present on the surface. So this is an overview of the subsurface radar sounder. It's operated at high frequency. It's lower than the SAR, but it's a so-called high frequency region at 9 megahertz. And it will search for boundaries of material, as I mentioned before, such as impact craters and their possible infilling with time as you get the erosion of the planet and you get the infilling of the craters, possible buried craters. It will also look at the tessera and their vertical structure and their buried edges. It will look at the plains and also look at lava flows and their edges. It also has an altimetry function, so it's less accurate than the SAR, but the subsurface sounder needs to know accurately the surface because you have effects called surface clutter where you get spurious reflections from the surface coming into your image, and that needs to be corrected for. So it's important for the subsurface radar to have a good knowledge of the surface topography. And it will penetrate the surface down to a maximum of 1,000 meters, more typically some 100 meters at the resolution of 20 meters. Again, you can see the specifications of the system here on the right and how it is looking on the left-hand side. Then we have the Venspec suite, and we start with the Venspec M, which is the push-through multispectral imager. And it's operating in 14 near-infrared transparency windows. So these are parts where the thermal emission of the surface can escape through the atmosphere and clouds. So at the bottom here, you can see which wavelength it is using. So these wavelengths over here are 0.86 micron up to 1.2 micron will be used to determine the mineralogy of the surface. So depending on the rock that you have on the surface, you will have different signal strength in the different windows, and they will have a different signature spectrally. And that can be used to really look at whether you're looking at basalts, rock, other types of rock, and maybe even granites, which would have been an indication that there would have been water on the surface in the distant past. It also is using some windows to look at clouds and cloud variability, because the variability of the cloud opacity can also give you some spurious variability of the surface signal, and that needs to be corrected for. And it also has a water channel to see the concentrations of water close to the surface, which is used for correction of the mineralogy product. It can also be used by itself to determine how much water there is close to the surface. So the mission looks at surface composition. It should look for volcanic activity. So you saw the temperature emissivity maps before from the Heritage mission Vertis on Venus Express. And hopefully we will be able to see such signatures again and to have revisit of those to get more conclusive results. The next one is the Venspec H, which is a high resolution spectrometer. It's looking in nadir towards the atmosphere, and it's doing really high spectral resolution observations in the shortwave infrared. So the figure here shows you the wavelength range here at the bottom and the radiance on the vertical. And the upper graph here shows you the sun-reflected signal that the instrument will be able to see on the day side of the planet. So it will only see down to the clouds, but the atmospheric species above the clouds that are absorbing and giving you these dips in the lines will be measured by the high spectral resolution instrument in different channels. As you can see here on the upper graph, on the upper part of the graph. It also looks at the night side of the thermal emission. So you have this very low, much lower intensity thermal emission spectra here on the bottom with different spectral windows, which will be used to measure SO2, water vapor, and also HDO ratios, and also minor trace gas species, which are related to volcanism. These are the accuracies here below. There is also some heritage from this instrument, for instance, from the Venus Express SOAR, instrument. And at the moment on ExoMars TGO, there's the NOMAD mission, which some of you are working on. And that's also having a similar, or having some heritage that are used again for the development of this Venspec H instrument. The last Venspec instrument is the Venspec U, looking at the ultraviolet. So it looks above the cloud deck in wavelength range from 190 nanometers over here up to about 380. At the lower part of the spectrum, it measures at very high spectral resolution in order to get measurements of SO and SO2. And whereas at the higher wavelengths, it has less spectral resolution. And here it wants to, they want to measure SO2, but also the so-called unknown absorber. So the Venus cloud deck is absorbing more UV light than what is expected from the known composition of the clouds today, which is sulfuric acid droplets, SO2 concentrations. And the question is, what is this very strong absorbing substance? The Venspec U instrument will look into and try and home in on that by measuring in the spectral range where this absorber is active. So we'll map the upper clouds and also give some information on aerosol properties from these observations, and you can also get information on cloud altitude. So then we come to the radio science experiment. So I was mentioning that before. It's using the radio link between the spacecraft and the Earth to determine, first of all, the Venus gravity field and the so-called K2 love number to constrain the internal structure of the planet. So the K2 love number is telling you how the gravity field is reacting to a body which is close by or circling the planet, such as a star or a moon or a spacecraft. And the lower the K2 number, actually, it tells you about the consistency or the homogeneity of the inner part of the planet. So if it's a low number, you probably have a solid core, and these observations will then be able to tell something about the inner structure of the planet. Also, you see here on the picture, when the spacecraft is moving behind the planet, it can we can look at the bending angle of the radio signal, and that will tell you about the temperature and the pressure composition of the atmosphere. And as it moves behind, you can look at it at different level. We'll measure between 35 and 90 kilometers, actually. These parameters you can see over here. So you can get sulfuric acid gas and liquid information, and also temperature and pressure information of the atmosphere. So the goal is really to look at the synergies, as I said before, to study the planet's history, activity, and climate. And this is yet again another sketch showing you how the different instruments are addressing the different application areas: gravity, geodesy, geology, and atmospheric chemistry, by measuring these different vertical scales below the surface down to 1,000 kilometers, and of course into the core up to 100 kilometers above the planet. But Envision will not be the only mission. In the 2030s, actually, flying to Venus. Another mission was selected almost at the same time at NASA. It's called Veritas. This is a slide from Stu Smith-Carr at JPL, who's the PI of the Veritas mission. And this mission will have a radar on board called VISAR. It's operated in X-band, and it will use INSAR capabilities to give very like a very good global coverage of topography on Venus down to 30 meters. So it's not going all the way down to 10 meters, but they're coming close. And it will be very interesting to look at the synergy between the Veritas topography that will be measured a couple of years before Envision will be there, and also how they envision topography maps to look at possible changes. On this platform, there is also an instrument called VEM, the Venus Emissivity Mapper. And this one is identical to our Venspec M instrument. So it will again look at surface emissivity in order to look for clues of active volcanism and also to do investigations of the rock types. And it has also gravity science experiment. Another one, which is also very exciting, which is measuring or will be launched a year after Veritas. I forgot to say that Veritas should be launched in 2028. And Da Vinci is scheduled to launch a year after. This is quite a different mission. It's actually an ascending probe mission. So it will be carried to Venus by a carrier, and then it will be dropped into the atmosphere, a bit similar to the early Venus missions in the 1970s and 80s, like the Venera mission. It will have a parachute, and then it will start to measure at 70 kilometers altitude as it goes through the cloud deck, and it goes all the way down to the surface. And when it comes below the cloud deck, it will also do very detailed imaging of the landing site at different resolutions. So it will measure both different gases as it descends, such as noble gas measurements in particular. It will also do some near infrared imaging to look at rock formation and have visual imaging. So that will be very exciting to see. These will be very accurate measurements, but at one specific location. And then you have the Global Envision and Veritas mission that will look at processes globally. There are also some other upcoming missions. One is from ISRO, the Indian Space Agency, and they are planning to launch a mission called Shukrayaan. And they've had an announcement of opportunity that I'm sure several of you are aware of to give the possibility for payloads from other countries also to be placed on this platform. And the selection of these payloads is ongoing right now. Hopefully we will know by the end of this year, or soon at least, what the final selection will be. And we know that there have been some responses from Russia, France, and Germany to this one for different instruments. And it's expected to launch still in the 2020s, actually, so before the other missions. There is also the Chinese Voice mission to study Venus, and that will be relatively similar to Envision and to the Veritas missions, more global missions with an orbiter. And also it's competing at the moment within the third strategic priority program in China. And this proposal is led by the Chinese Academy of Science. And the selection of the missions to go forward in this program are expected to be also quite soon, probably within this year. They have a very ambitious launch target, which is 2026. So that's actually going to be pretty soon, should this mission be selected. There is also another proposal for a lander on the Russian side called Venera D. So that is actually having different modules, an orbiter, an aerial platform, as you can see over here, and also a landing module. And that's a slide lifted from a presentation from Roscosmos and IKI on this mission. So we're now really looking at the possibility to pave the way for a decade of Venus in the 2030s, and even before that, there will be several missions. And people are working on Venus science are very happy about this because there have been many missions to Mars over the last couple of decades, I think around 30 or so, whereas in Venus there have only been a few. And we're happy to see that there is now a number of Venus missions in the making. And this will be very complementary. For instance, we will be able to have, as I mentioned before, multi-year radar imaging to look at the surface, the topography and possible change detection. That will, we can compare then the older Magellan data set with Veritas and the Vision data sets in the future. Also, there will be multi-year observations of the atmosphere composition and dynamics. And this we have from the Venera and Pioneer missions in the 1970s and 80s. We had Venus Express, Akatsuki mission, and also the future Da Vinci and Vision missions. So these really give you a time span over many years, also giving different observations of the atmosphere. And then we have the gravity observations consolidating the models of the inner core of Venus and the planet's interior. And there, of course, earlier missions such as Pioneer Orbiter from NASA in the late 1970s. These data sets can be compared with the radio science experiments on Magellan, Venus Express, and also the upcoming missions. But Envision will also have some firsts, despite of all of these different missions coming up. It will be the first one to simultaneously study the Venus surface, interior, and atmosphere. As I said, the other missions are not doing that so completely. Perhaps the Chinese voice mission will, but we will see what comes out from their selection in the end. And perhaps also the Indian mission. We have to see also which payloads will go on there. It will, however, be the first one to do subsurface sounding, and it will also go down to quite high resolution, as fine as 10 kilometers for certain regions of interest. It will be the first polarimetric radar imaging the Venus surface. We have to see again if the voice mission will be selected and also do something similar, but that's still to be confirmed. Also, it will give for the first time profiling of sulfuric acid droplets. That's not been done before, and also do the synchronized search for volcanism. It will also be the first orbiter with a dedicated search for geological change. So coming at the end to the status. So the mission was was selected last year, and it will have a final adoption in 2024. The final concept will then be ready, and ESA will then have an adoption phase to really give the go ahead for the building of the hardware and the software, and to develop it to be ready for launch in late 2031. And it will also have launch opportunities every 6 months after that until May 2033, should the first launch window not be possible for some reason. The cruise phase of the spacecraft, so you can see the launch here, and it needs to cruise, of course, to go to Venus, will be about between half a year and 1.5 years. That depends on the actual launch date and also the launching strategy, which is being consolidated as we speak. Then there will be an aerobraking phase, so the spacecraft comes there and it will be in a highly elliptic orbit, and then it will use the Venus atmosphere to brake in order to come into the final orbit that we will have. And the platform data will also be available for possible scientific investigation, and Gabriela in the room here is looking into that right now at the moment to see what we can do with this data. And the mission total lifetime, as I mentioned before, is 4 Earth years, but it could possibly be longer as well if it would be extended. So the competing consortia right now, we have 2 industry consortia working on the platform concept and the mission concept, and these are Airbus Defence and Space and Thales Alenia in Italy. Airbus Defence and Space, UK is the prime, Italy for Thales Alenia is the prime in the industry consortium side. So coming to the conclusions, Envision will be a dedicated study, or will allow a dedicated study of the geological activity and history of Venus, as I've told you today, and its influence on the atmosphere, possibly also the other way around, the heavy atmosphere also working on the interiors of the platform of the planet. It's built on heritage missions from before. It also has some novelties, and it will be crucial for making a step forward in understanding planets, not only in the solar system, but also beyond that. So it's very interesting to compare Mars, Earth, and Venus and how they have developed differently in time, and in order to use that to understand how exoplanet systems also are different and if they can be habitable. So, as said at the start, EnVision will help us understand why our closest neighbor is so different. So with this, thank you for your attention.
Much for your very complete presentation of Venus as introduction and the possibilities and opportunity that we have in the next decade. Take questions. I don't know if there are questions on Zoom. We can move. Do you have questions?
There is no question on Zoom by now, but I will tell you.
I have.
Okay, Lisa.
Yeah. Hello. Good morning. I'm Lisa. I my camera because I am with Wi-Fi at home. Since there are several very high resolution.
Cannot hear Lisa.
We cannot hear now.
Sorry.
We cannot hear you very well, actually, at all.
Okay. Now better.
No.
Hmm.
Rene, can you talk?
Yes, but I cannot hear Luisa either.
The problem is in her on her side. So.
Yeah.
Now.
Yeah.
Yeah.
Okay. So, well, I'm Luisa, and working at the institute. I don't switch off my camera because I am with Wi-Fi at home. The question is related to the spectrometers. Since you have very high resolution, or we are going to have very high spectral resolution spectrometers, when you measure any of the gases, can you constrain the isotopic ratios and saying something about the volcanic origin or the interior or the surface, or is not possible? I mean, you know, the point is there any isotopic ratio characteristic of volcanic eruptions that we can discriminate from what is in the atmosphere?
So I have to say that I'm probably too new to this in order to answer that question. To my knowledge, there is not. I mean, the gases that will be measured in the spectral bands is given over here, and the spectral resolution will be quite high. But whether that can be determined, I'm not certain. What is certain is that the instrument is sensitive to the lowest 15 kilometers, for instance, of the atmosphere. We'll be able to look at these trace gas concentrations really close to the surface. So hopefully, if you have an eruption at the time it's flying, you can see the eruption in the Ventspec M instrument. You can see also some signature back in the Ventspec H spectra. But really to hone down on the processes for the surface, I cannot answer, I'm afraid. I think not. Maybe you.
Well, I think
It's okay.
We can hear you.
no. Now that you're talking, that points that my understanding of this issue is kind of similar to what happens on Mars. One of the interesting gases which might demonstrate kind of volcanic activity at present is SO2 because of these variations. So because the isotopic abundances are very affected by the long-term evolution of Venus at present, if there were any variation in time during the mission, one of them might indicate some refreshment from, some fresh emissions from below. So that might be one possibility, to track the isotopic abundances and see variations on them during the mission, because that had to be from something, a fresh source. That's my mission. If nothing is obtained, it doesn't mean there are no sources, but if something is seen in that direction, it might be just because of the contrast to the current isotopic abundances, which only track a very long-term margin. That's my understanding. So there is a possibility.
Yeah, thank you for that clarification. Very good.
Francisco, you want to ask?
Yeah. Some of the payload that Envision is going to have is similar to, for example, the radar, the subsurface radar or the radio science instrument is similar to some payload that is being used on Mars to study the ionosphere, for example. So are there plans to look at the ionosphere, even if it's not in the main goals of the mission?
So what I've understood, again, I'm not the expert here, is that this particular wavelength is not that sensitive to the ionosphere, and that's also in order to have good subsurface information due to the atmosphere on Venus being much different, much denser than on Mars. However, there are some investigations at the moment from the Italian team to see whether you can do some science on the ionosphere with this instrument. And also they're looking into the possibility to perhaps detect lightning from Whistlers also, but it's ongoing work. So to be in listening mode, but it is not clear that anything really substantial can be found there yet. So it's under investigation.
Thank you.
And is there also possibility with the radio occultation? There was a presentation by Sylvia Tauer and CSC, and she proposed also to measure electron density with radio occultation. It was not on the goal mission, but it's still on the table, I think.
Indeed, and what's important is anyway to do ionospheric correction of the radio occultation signal. So they will start to measure just before entering the ionosphere and going behind it. So there will be detection of the ionosphere. So I'm expecting that this can be done as well.
Any more questions? Could you please come closer? Just.
I was just wondering about the aerobraking phase, and well, Europe has some experience with aerobraking, with Vision Express, for example, etc. And so I was wondering if, in addition to Envision, are the other missions from the US planning also aerobraking or not? And
Definitely.
then in relation, yeah, they are right. Okay.
Yes, so the Veritas mission, for example, that's going to have quite a low orbit. So that will be orbiting at around, if I remember correctly, 250 kilometer altitude or something thereabouts. Maybe it's written here. And they will use aerobraking as well in order to come down to that altitude, and they will have a very circular orbit. So there will be also data from that mission as well on aerobraking that will be used. Actually, at the moment, ESA and NASA are discussing together a little bit the models of the atmosphere. ESA's had a study with LMD to extend the global circulation model that they have up to higher altitude, so that they can do more precise calculations and preparations for the aerobraking, which is very delicate for the mission. And we're also discussing with NASA how they're doing that and the models that they're using for that.
That's great. And in relation with that, it caught my attention that the orbit is not exactly circular, right?
Exactly.
So, why is that? Is there any reason?
So you have different instruments on board with different requirements. Some want to be closer to the atmosphere, some want to be further away. And also, like the radio science experiment, Venus Express was having a very elliptic orbit. So it was mostly the southern hemisphere observed. Now one would like to cover the northern hemisphere, but still have some variability in the altitude also for some of the payloads. So it's a compromise and as well, we would like to have a longer mission lifetime than Veritas, so really 4 years instead of, I think it is about 2 years for Veritas, normal time. By going a little bit higher in parts of the orbit, you can increase the lifetime with having less air or braking by the atmosphere. So there are different reasons why it's slightly elliptic.
Well, my last question or comment is that I'm so glad, like the whole community, that we are going to win it. I won't have any complaint, but if I had one, if I had, that I don't, I will say that what a pity that we go the last ones in the queue, no? Because we are arriving 2031 or something, no? And so these synergies means that some of the discoveries may be done before by others, I don't know, but it doesn't matter because in the end also it has advantages. You can build up long-term mapping on Venus, which is good. Actually, if I had to choose from outside view regarding these selfish European discoveries, I would prefer to have missions which really track Venus for the long term as much as possible. So that is good in that sense. But and I wonder, question is, it's going to be really overlapping emissions, because that would be also very interesting.
That would be very interesting. And if Veritas, for instance, has an extension, then there could be some overlap with Envision and Veritas also, provided that we go in the earlier launch date phases. That depends a bit on exactly how long the missions can last in their orbit. So that would be great to have at least overlap between these two. The other earlier missions by the Indians and the Chinese, I believe that these would be finished before Veritas is launching, but I don't have all the orbit parameters for these yet, so I can't really tell you exactly how they will fly, but I'm expecting it will be similar to Veritas and Envision in one way or the other. So yes, it would have been nice to be faster. I think one of the challenges for Envision, it's a large mission with many instruments that need to be ready on time. And if you go for a smaller mission, or if you have much more money available, you can also go faster. So it's a function of availability and complexity, I would say.
We can close here, even if maybe there are many more questions for Andre. We can ask her during tapas if you want to join us. Let's thank Andre again for the nice overview. Thank you.